This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the different types of traversals on binary search trees and their time complexity analysis. There are three types of traversals, including the in-order traversal, pre-order traversal, and post-order traversal. We will start with the in-order traversal. The purpose of all the three types of traversals, including the in-order traversal, is to visit every node in a binary search tree. In-order traversal is a recursive function that involves a few steps, mainly including traversing the left subtree, visiting or processing the current node, and traversing the right subtree. It goes over these three different steps on every node in the binary search tree. Instead of applying these steps to an example directly, it's better that we translate the steps to pseudocode first, as many people struggle to understand how it works without seeing the placement of the recursions. Translating these steps to pseudocode, you will have this. This function is named in-order traversal, and it takes a single parameter representing the current node it's being dealt with. The first few lines underneath this function deals with the base case. The base case is about when to end the execution of the in-order traversal. These three lines, they correspond to these steps we covered. So for every node, it will start by recursively traverse its left subtree. After that, it will visit the current node. In the end, it will recursively traverse the right subtree of the current node. This visit method here is a helper method whose definition is up to you. You can define it in any way that suits your needs, such as printing the value or storing the value into an array. With the help of the pseudocode, let's go over an example to make sense of the in-order traversal. For demonstration purpose, we will call the in-order traversal function on the root node. I mean the root node of the binary search tree sits on your left side, and we will process the value of each node by storing it into a prepared array, like this one. While this array is empty, it comes with the same size as the binary search tree example on top of it. Based on the pseudocode, we will first visit the left subtree of the root, then process the root node. After that, we will visit its right subtree. Remember, the function starts with a recursive call and ends with another. It does the same to every node. For every node, it will visit the corresponding left subtree, process the node, then visit its right subtree. If you want an execution order of different nodes in the left subtree of this example, it looks like this. Now let's go over the execution order one node after another for at least the left subtree. Node 20 is the first node to be processed, or say its value will be the first one to be stored into this array, because it is at the most left side, like this. After that, the whole left subtree of node 31 will be visited. So you will move to process the node of 31 by copying its value into the array, like this. After that, you will visit the right subtree of node 31. You may think that it's the turn of node 41 now, but you need to wait because the node 41 has a left subtree. So you have to visit all the nodes in its left subtree before you ever start processing the node of 41. Okay? So you will start with the node 32. Node 32 doesn't have any left child, or say it doesn't have a left subtree. So it's a turn to process the node 32 by storing its value into the array, like this. After visiting the node of 32, it's the time to visit its right subtree now. So the next will be the turn of node 34. The next will be the node 36, like this. After that, it will be the turn of node 41 to be processed. You will write its value to the array, like this. Now you have visited every node in the left subtree of the root node. It is finally the turn to process the root node. Same, you will write its value or say copying its value to the array that we prepared, like this. Well, for simplicity, I won't go over each node in the right subtree. The same steps would be applied to every node in the right subtree. For every node, you will visit its left subtree, then process the node, then visit its right subtree afterward. In the end, you will get every node processed or see their values copied into this prepared array. As you can see, the array is perfectly sorted in an ascending order. That's what in-order traversal will be able to do for you. Because of the nature of binary search tree, when you run in-order traversal on one and store the values into a linear storage, you will always end up with a sorted data structure. That's exactly why binary search tree is not only useful for searching, but also useful for sorting. Beyond in-order traversal, there are also two other types of traversals, the preorder one and the post-order one. Let's look at both of them. The preorder traversal changes the order of these three lines and makes processing each node the priority, and pushes the two recursive calls to the end. In contrast, the post-order traversal makes the two recursive calls the priority and pushes the processing of the current node to the last task. As you can imagine, these two types of traversals won't lead to a sorted linear data structure, but they are still useful in their own ways. When you need to capture the tree structure for reconstruction or process root-first tasks, preorder traversal is typically the one tool to use. When you need to do some teardown tasks or bottom-up evaluations, post-order traversals will be very useful. As for the time complexity of the binary search tree traversal, they are all the same. Since you need to visit each node only for once, the time complexity of each type of the traversal is simply big O of n. Expressed as Tn belongs to big O of n. In this video, we learned about the different types of traversals on binary search trees. That's everything of this video. Hope you learned something new.